All right.
Everyone says
You guys ready?
Wait, hold on.
there were two signals that you also 2 weeks ago. But it's not Chinese. Two that
All right.
I was going 106.
We're gonna start. This is a system of equations. You have two equations because there are two unknowns. You have to have two equations if you're trying to solve for two unknowns. We've already gone over how to solve systems of equations. So you already have two methods of solving this system. You have the substitution method, and you have the elimination method. So you already can solve these. However, you'll notice that there are systems on this worksheet that have three variables, x, y, and z. Therefore, they require three equations. And I don't believe that you guys have solved a 3x3 system before. So you're used to two-dimensional systems. But the method that I'm going to show you today will work for the two-dimensional systems. You kind of don't need it because you already have other methods. But the three-variable systems are harder. And I think this method might be the easiest method for solving them. I don't know. That's just a relative opinion. Other people might disagree, but I think this is easier. So it's going to use determinants like we did on the last worksheet. And we're going to be able to use determinants. Cramer's rule allows you to use determinants to solve systems of equations for the x and y and even z. So again, you could solve this like you normally did. I'll do a different color. Like you could say, well, if I subtract 5x from both sides, I could rewrite the second one as y is equal to 6 minus 5x. And then I could put this 6 minus 5x into where y was, and I could solve that way. That was substitution. We also had elimination. I could have multiplied all these numbers by 6. And then I could subtract, and I could eliminate the y's, and then I could solve it that way too. So you already have ways of solving this. This is yet another way, and it will extend to three variables just fine. All right, so what we want to do is we're going to come up with three matrices in this case. It doesn't really matter what they're called. Sometimes I call them D for determinant. But one matrix will be, you'll write it like this. And these just represent, the first column represents the coefficients on the x terms. And these, the next column represents the coefficients on the y terms. This is called the coefficient matrix. And you just take the coefficients on the x and y terms, and that makes the matrix. You're also going to find two other matrices. I'll call this dx. You're going to rewrite the same matrix. I'll do that. But when you're building the one to solve for the x variable, you're going to actually replace the x coefficients. I'll choose a color. And you're going to put in these other two numbers in for the x coefficients. So I'm going to put 4 and 6 there. For the y, you're going to do the same thing. You're going to have -2 and 5 in the first column. But for the y coefficients, you're going to replace those with 4 and 6. Is this okay so far? I've just taken the coefficients and I made one matrix, and then I made two other matrices just like it, but I put 4 and 6 either in for the x column or for the y column. So hopefully that's okay. And so the way you can solve for x is take the determinant of the dx matrix divided by the determinant of the coefficient matrix. That'll be your answer for the x. And for y, you just take the determinant of the y matrix divided by the coefficient matrix. So I'm going to do that, and hopefully it makes some sense. The determinant of the x matrix over the determinant of the coefficient. And if you recall, the taking determinant of the matrix was you multiply this diagonal, 4 and 1, and subtract the product of this diagonal. And over in the one underneath, you'd have negative 2 times 1 minus 6 times 5. And so I would get that x has to be equal to, what is this? 4 minus 36. So I'm going to get a negative 32 on top. And on the bottom, I'll have negative 2 minus 30. So I get a negative 32. So x is equal to 1 in this case. Is that okay? You guys follow that? All right, I'm going to do the y. It's this matrix over the coefficient matrix. And that's just negative 2 times 6. So that's negative 12 minus 20. And I'll have negative 2 minus 30. This is the same as over here, so I'm going to get the same denominator. And that's, once again, negative 32 over negative 32. So y is also 1. And so they'll write their answer as an ordered pair, x and y. They'll just write that. Any questions on that one? Is that okay? All right, I'll do number 2. And let's see if you guys can remember kind of what we just did. 2 times r plus 3 times s. This is just like x and y. They're just using r and s. Equals minus 12. And minus 6r minus 2s equals 7. Equals 7. All right, what's my coefficient matrix going to be? Anybody got that?
Negative 6 over negative 2.
What was that?
Is it 6 over, like, negative 6 over negative 2?
No. You're just going to take the coefficients, right? Do you see these numbers in front of the r and the s?
Yeah.
It's just those numbers. So I'm going to say 2 and then negative 6 and then 3 and negative 2. So I just took them from here. One of the things you have to do with this method is make sure that your equations are in this homogeneous form where you've got the r's lined up, the s's lined up, and everything's sort of in order, all on the left side with a plain number on the right. So we'll take that matrix and we'll need the determinant of that eventually. We'll have the x matrix, which is going to be the same matrix, but instead of the x column, what am I going to put instead of the 2 and the negative 6? These will be the same, but what should go here?
negative 12, 7.
Good, good. Yes? And then for the y matrix, the x's will be the same. But now you're going to put the negative 12 and 7 in for the y. That's a 7. Is that okay? Are we good on that? All right. Who thinks I can do the determinant of the coefficient matrix, D? What do you get for that? Anybody want to try? How do I take a determinant? A 2 by 2. Remember, it's just,
Sorry.
yeah. Those will be one of them. And then these are the other one. So you have the 2, negative 2, and you'll subtract 3, and negative 6. So that would give me negative 4 plus 18. So what did I say? Negative 4 plus 18. So is that 14? All right, now I'm going to do, I'll just do these so that they're there. So I will get negative 12 times negative 2. That makes 24. I'll just write. And 3 goes to 7. So negative 20, or positive 24 minus 21. So that should be 3. And then finally, you have 14 minus negative 12 and minus 6. So that's going to make 4. That's going to make 14. And 3 negatives is a negative. So we're going to say 14 minus, what is that, 72? What is 14 minus 72? 58. Is that right? Negative 58, right? Yeah, 14 minus 72 is negative 58. And so my answers would be for R. I guess I should have called these dr and ds because we're using R and S. So I'm going to put 3 over 14. And for S, I'm going to put negative 58 over 14. And that will reduce, what does that fraction reduce to? 58 over 14. The bottom is like 72, right? What's that? Does it have a 2? $29, is that right? Did I do that right? Did you need something? Okay.
So would it be negative?
Yeah, it's negative, yeah. Is it 29? Is that right?
Yeah.
So I can cancel 2's. So negative 29/7. Yeah, and you can, you do have the answers that you can check, right? Yeah, that's correct. So we got those ones correct. Is that okay? All right, I'd like to do one of these harder ones. They have the 3 variables. So it's a little more involved, but it's the same idea in practice. Just like before, this time when you have 3 variables, you're gonna need not 3 matrices, but 4. You're gonna have the coefficient matrix, and you're gonna have 1 for each variable, x, y, and z. The x will be the x matrix over the coefficient, the y will be the y matrix over the coefficient matrix, and the z will be the z1 over the coefficient matrix. So let me do, this is problem 13. Let me scroll, sorry. So I'm going to do this problem. That was 5x plus 2y plus 2z equals 9. Negative 6x minus 4y minus 3z is negative 19. And then they have x minus 2y is equal to negative 9. So they don't have a z term here. You can think of that as 0 z's. So if you're missing one, that's a 0. So that's one thing to keep in mind. If you don't have a variable in one of the equations, there's a 0 times that variable there. So I will have a coefficient matrix. I'm just taking the x column, the y column, and the z column. And I'm going to want to find the determinant of that. I guess I'll write the other ones. Dx will be, I'm going to replace the x column with these numbers. The other columns stay the same. And I'll do this one, and then we'll go back and do the dy and the dz because this one's going to take up more room. So I'm going to start here. So what I'm going to do is I'm going to copy the first 2 columns. I'm going to make duplicates of those. And now I can make diagonals. So again, this is for the 3x3s. It's a little bit more involved, but it's the same basic idea as before. You're going to have these diagonals are the positive contributions, and I'll choose a different color. These are going to be the negative contributions that will subtract. It's always nice to get a 0 in there because you know anything times 0 is 0, so you don't have to worry about those ones when they have a 0 in there. All right, so 5 times negative 4 times 0 makes 0. 2 times negative 3 times 1 makes negative 6. Well, good, how are you?
Good.
And then 2 times negative 2 makes negative 4, times negative 6 makes 24. So that's those diagonals. Going the other way, we get negative contributions. You have negative 4 times 2. It's negative 8. So I'm going to subtract negative 8. Negative 2 times negative 3 makes 6. Times 5 makes 30. And then this has a 0 in it, so anything times 0 is 0, so I don't have to worry about that. So altogether, the determinant of that matrix, I don't know. What is that? I'll just do that on my calculator because I'm lazy. Negative 30 plus 8 plus 24 minus 6. So I got negative 4. I'll do the same for this one. And I'm just going to kind of use my calculator because these are getting, the bigger the numbers get, the less I want to do them in my head. So I will get 9 times negative 4 times 0. I'll just write everything. We'll have 2 times negative 3 times negative 9. And then 2 times negative 19 times negative 2. Those are the 3 diagonals that way. And then I've got the 3 diagonals going the other way. So I'll have negative minus. Actually, I'll put these below. Minus negative 9, negative 4 and 2. Minus negative 2, negative 3 and 9. Minus 0 times negative 19 times 2. Altogether, that's a 0 term, that's a 0 term. Only got to worry about these 4. So that gives me, what is 9 times 3 times 2 plus 19 times 2 times 2. This will end up being a minus 9 times 4 times 2, another minus 2 times 3 times 9, and hopefully I did that right. I got 4. So I now know that x should be 4 over negative 4. Which is negative 1. So it's much more spelled out, but this method does work on 3 variable equations as well as 2. So you can now solve for 3 variables, which you haven't been able to before, with this method. Any questions so far? This seem okay? Now, once you have one of the variables, notice this equation that I had here. It relates, because there's no z term, basically. There's no z's in that. So it relates y and x. So if I know x, which I do now, that means I know y. I know that x has to be, if x is negative 1, then this equation has to be true when I plug in negative 1 for x. So if I solve for y, I add 1 to both sides. I'll get negative 8 over here. And then I'll divide by negative 2. I should get 4 for y. Is that okay? So, I mean, you could go through and do the whole matrix for y, but once I had x, I didn't need to. And now that I have x and y, I can use one of the other equations, maybe this one, and I can figure out what z is. So I'm going to use green maybe. And I'll come down here, and I'm just going to plug in -1 for x. I'm going to plug in 4 for y. And I'm going to solve for z. So this is -5, and that's 8. So together they make 3. Subtract 3 from both sides, you'll get 6 over here. 6 divided by 2 is 3. So I have x is -1, y is 4, and z is 3. So I could have done matrices the whole way through, but once I got one of the answers, I really didn't need to. You can just start plugging in, figuring out the rest of them. Is that okay? You guys following this? I hope. All right. Maybe I'll try 9 so that you can kind of see what happens in certain cases. One thing you'll notice about all these systems is there's no x squared, there's no y squared. These are all linear, they're called. These are linear equations, which means that each equation represents a line. If you graphed it, it represents a line. So there's 3 scenarios. You might remember this from Algebra 1 or from solving equations homework. If you have 2 lines in a 2-variable system, your lines could be, if they're different lines, if you have 2 different lines, there's a possible solution. So you'll have a coordinate, like maybe it's like 10 comma, I don't know, 9. You'll have some point that's the solution where the lines cross. So you might have one solution, and most of the questions you'll get will have a solution. There could be the case where the lines are parallel and they never cross. And in that case, you'll have 0 solutions. The other situation you could have is where the 2 lines, when you graph them, they might look different, but when you graph them, you get the exact same line. They completely coincide. And in that case, we would say infinitely many solutions, or infinity solutions. So here, every single point is a solution because they cross everywhere. They're the same line. Here, they don't ever cross. There's no solution. And here, there's one solution. These are the 3 possibilities. So this question that we're going to do now, I'm looking at the answers. It'll have no solutions. So I'll show you what that looks like in this method when there's no solutions. Yeah, I'm doing number 9. All right. So what happens in this one when there's going to be no solutions possible? Well, I'm going to write my matrices. And then I'll have a dx matrix, which will be -12 and 11, and then 2 and -1. And then I'll have a dy matrix, which will be -2 and 1, and -12 and 11. And I think we'll see it here in the first matrix when we take that determinant. And what we will see is that I get 2 minus 2. So I'm going to get 0. But remember, the determinant of the coefficient matrix is in the denominator of my other matrices. So X is going to be the determinant of the X matrix over the determinant of the coefficient matrix. And then that means you're going to have to put 0 here. And you can't have division by 0. So there's no X solution. And it's the same with the Y. You'll take whatever the determinant is of this matrix, you would divide it by the 0, and you can't. So no solutions. A lot of times we'll put the empty set to show that there's nothing, there is no answer. So when this first matrix, when you take the determinant, the coefficient matrix, and the determinant is 0, that means no solutions. So that one, that's what happens when there are no solutions. Is that okay? All right, I'm going to do number 3 as well, because that is an example where there will be infinitely many solutions. So I'll show you what happens in that case.
Can't you just like figure it out for the problem? You could like you can see how this would be.
Yeah, notice they're the same equation, just with the signs flipped. Yeah, if they were the same equation, but everything was scaled by the same number, so if all the numbers were doubled,
Yeah.
then yeah, they are the same equation.
No, and it's in there like the 9 all of them will equal 1, so it should be 1, 1, 1, 1, 1.
Well, no, that one, they're not the same, because
Well, no, I know for number 9 because they're all equal 1. Will they for the no solutions one?
wouldn't all equal 1.
Yeah, like negative 2a, and then like put them together.
Oh,
How
yeah.
they'd all equal 1, so they're like no.
No,
solution.
it's when they're almost the same equation, but that extra number is not the same. That's when they're basically parallel lines, but that they don't intersect.
Okay.
One's above the other, so they'll never cross. These ones overlap entirely, like number 3.
Yeah, I know.
So that one, I'm kind of curious how this is going to break down. I don't remember doing these actually with Cramer's rule when you have infinitely many solutions, so I'd like to see what happens. So the determinant matrix is -2 and 2, -4 and 4. Let's see what that gives me. I get -8 minus a -8, so 0. So I got 0 again. So how would I know that this has infinitely many solutions instead of no solutions? I guess probably the other matrices will be actual, they might be 0 as well. I think they will be. So if I did -16 and 16, and then -4 and 4, I'll get -16 times 4 minus -4 times 16. So these also come out to 0. So in this case, x would be not a number over 0, but 0 over 0. And I guess that is going to be your indication that this technically isn't a legal construction. You can't have division by 0. But 0 over 0 is kind of a weird one. I guess in this case, it's going to let you know that you have infinitely many solutions. Is that okay? And I'm guessing y, you'll get the same thing. You'll get the dy, that should come out to 0 as well. Let's see.
I go to the bathroom.
Yes. All right, so any questions, or you want to see any more of these, or are you guys good? All right, well, I'll give you time to work on it then. And then I'll upload this video so you have it. How are you, Abby and Zoe? Are you guys good? All right. Well, you don't have to stay on unless you have questions. Let me know. Otherwise, you can just work on these. I'm going to stop presenting too. Okay, that's fine. Yeah, I'm going to close the call, and then once I close it, they'll send me the video. After it processes, I'll upload it to YouTube and put that in the playlist as well for you. So, all right, have a good day.